Welcome back! Today we're diving deep into the world of multimeters, focusing on their application with VFDs and motors. Let's begin by exploring our setup. Here we have a demo unit representing a VFD drive with an input power box on the left, an output power box on the right, and a three-phase motor. Let's go ahead and measure the input voltage. Set the multimeter to the volts AC function and connect the test leads. Now take the probes and connect them to the test points at the input box. Observe the reading on the display. As you can see, the input voltage going into the VFD is 120 volts. A VFD operates on single-phase input power and converts it into three-phase output power to run an induction motor. And if we take a look at the display on our VFD, we can tell that the output voltage is set to 230 volts. Now let's go ahead and check the voltage of the output of the VFD. Reconnect the test probes across L1 and L2 terminals. Observe the reading on the display. As you can see, the output voltage we're reading is 255 volts instead of 230 we see on the VDF's display. That's because motor drives transform the standard sine wave into a PWM signal. A typical multimeter might not capture this accurately. To get an accurate reading, activate the low-pass function on your multimeter. Observe the reading on the display once again. The low-pass function filters out high-frequency noise and interference, allowing the multimeter to accurately capture the fundamental value of the PWM signal. This is why the new measurement is more representative of the actual voltage. Now let's discuss the frequency measurement function. Circuits and equipment may be designed to operate at a fixed or variable frequency. They may perform abnormally if operated at a different frequency than specified. For example, an AC motor designed to operate at 60 Hz operates slower if the frequency is less than 60 Hz, or faster if the frequency exceeds 60 Hz. For AC motors, any change in frequency causes a proportional change in motor speed. A 5% reduction in frequency yields a 5% reduction in motor speed. Now go ahead and adjust the frequency knob and set the frequency to about 30 Hz. With the multimeter still connected to the circuit, let's briefly deactivate the low-pass filter function and press the Hertz button to enter a frequency measurement mode. Observe the reading from the display. As in the previous example, the reading is now accurate due to the nature of the PWM signal. Now let's bring back the low-pass filter. With the low-pass filter on, we now have a more accurate representation of the actual frequency value. So when testing VFDs, remember to use the low-pass filter setting for accurate readings. Now, let's explore the duty cycle. It represents the percent on versus the percent off of a signal. With the multimeter still connected to the circuit, press the Hertz button once again to enter a duty cycle measurement mode. A measurement of 25 is a signal that is on 25% of the time and off the other 75%. Having this information might be handy when analyzing the waveform to see if it's symmetrical or if you have a square wave. Now, let's switch our focus to another important function of the multimeter, measuring current. To measure current, one common method involves connecting the multimeter in series with one of the motor's phases. We will use the test terminals on our demonstration panel which simulate a break in one of the phases, allowing for our multimeter to be connected in series. But first, let's set the multimeter to an amps function. Connect the test leads to the corresponding input jacks. A black test lead to the COM jack and a red test lead to an amps jack. Notice that the multimeter has 2 amp input jacks. They have different range and different fuses protecting them, so when measuring unknown current, be sure to use the input jack with the higher range value first to protect the multimeter and yourself from accidents. Now take the probes and connect them to the test points at the input box. Observe how the current flows from the VFD through the multimeter and into the motor. When measuring current with this method, you have to consider that full power is traveling through the multimeter, which poses a great risk to the person using the multimeter, and any unexpected changes in the system parameters, like transients, will affect the multimeter too. This brings us to the clamp accessory, a safer and more convenient method for measuring current. Connect the clamp accessory to the input jacks. Now take the clamp and mount it around the improvised coil on the output box. In general, AC clamp meters operate on the principle of a current transformer used to pick up magnetic flux generated as a result of current flowing through a conductor. Assuming a current flowing through a conductor to be the primary current, you can obtain a current proportional to the primary current by electromagnetic induction from the secondary side winding of the transformer, which is connected to a measuring circuit of the instrument. You've done an excellent job mastering the multimeter's use with the VFD and motor. Remember, the right tools and methods can make all the difference. Thank you for participating in this training, and see you in the next one.